There is a place in the universe so empty, so vast, and so strange that it might be tearing reality apart. And the most unsettling part, you are inside it right now. Every star you see, every galaxy astronomers have photographed, the very ground beneath your feet, all of it exists within a cosmic emptiness that scientists believe is breaking the fundamental rules of how the universe should work. This is not science fiction. This is not a theory waiting to be proven. Observations from the most powerful telescopes ever built suggest that our corner of the cosmos is not like the rest. We live in a void, a supervoid, a bubble of nothingness stretching nearly 2 billion light years across. And this emptiness is doing something that physicists cannot fully explain. It is making the universe expand faster than it should. It is creating a tension in our understanding of reality itself, a tension that, if left unresolved, could force us to rewrite everything we thought we knew about space, time, and the ultimate fate of existence. If this sounds like the kind of thing that should keep scientists awake at night, that is because it does. Before we go any further, if you find yourself drawn to the mysteries of the cosmos and want to explore more stories like this one, take a moment to hit that subscribe button and give this video a like. It helps us bring you more journeys through the strange and wonderful universe we call home. Now, to understand why living inside a cosmic void is such a profound problem, we need to step back and look at the biggest picture imaginable. We need to see the universe not as a collection of stars and planets, but as something far more intricate. Something that looks, from the right distance, like a web, a cosmic web. When you look up at the night sky, you see points of light scattered across the darkness. It appears random, chaotic, beautiful, but without obvious pattern. This is an illusion created by our limited perspective. We are like ants standing on a single thread of an enormous spider web, unable to see the grand structure that surrounds us. But astronomers, using decades of observations and powerful computer simulations, have mapped what the universe actually looks like on the largest scales. And what they found is breathtaking. The universe is not a random scattering of galaxies floating through empty space. Instead, galaxies are organized into a vast network of structures. Imagine taking a sponge, the kind you might use to wash dishes, and stretching it to cosmic proportions. The solid parts of the sponge would represent where matter has gathered, forming galaxies, groups of galaxies, clusters and superclusters. The holes in the sponge would represent the voids, vast regions where almost nothing exists at all. This is the cosmic web. It is the largest structure in the known universe, and understanding it is essential to understanding our place within it. Let us break down the components of this web, starting with the densest regions. At the intersections of the cosmic web, where multiple strands come together, you find galaxy clusters. These are gravitationally bound collections of hundreds or even thousands of galaxies, all orbiting a common center of mass. The Virgo cluster, located about 54 million light years from Earth, is one such gathering. It contains over 1,000 galaxies and exerts such gravitational influence that it pulls our own local group of galaxies toward it. But clusters are just the nodes in a much larger network. Connecting these nodes are structures called filaments. These are long, thin strands of galaxies, dark matter, and gas that stretch across hundreds of millions of light years. Think of them as the highways of the cosmos, channels along which matter flows from one region to another. When astronomers map the positions of millions of galaxies, these filaments appear as glowing threads connecting the bright points of clusters. Then there are walls, which are essentially flattened versions of filaments. Instead of being thread-like, Walls are sheet-like structures where galaxies have accumulated in two-dimensional arrangements. The Sloan Great Wall, discovered in 2003, is one of the largest known structures in the universe. It stretches for over 1 billion light years and contains countless galaxies arranged in a vast cosmic curtain. But here is where things get interesting, and where our story truly begins. Between all these filaments, clusters, and walls, there exists something else. Or rather, nothing else. The voids. Cosmic voids are exactly what they sound like. They are regions of space that are almost completely empty. Not just empty of stars and planets, but empty of galaxies, gas, and even dark matter. While the rest of the universe has been gathering into the dense structures of the cosmic web, these voids have been doing the opposite. They have been emptying out, becoming more and more sparse as time goes on. The typical cosmic void is enormous. We are talking about regions that span hundreds of millions of light years across. To put that in perspective, the Milky Way galaxy is about 100,000 light years in diameter. A typical void could fit tens of thousands of Milky Ways inside it, with room to spare. And yet, despite their size, voids are eerily empty. Some contain only a handful of galaxies, lonely islands of light floating in an ocean of darkness. The first voids were discovered in the late 1970s and early 1980s, when astronomers began conducting large-scale surveys of galaxy positions. Before this, scientists had assumed that galaxies were more or less evenly distributed throughout space, like raisins scattered randomly through a cake. But when they plotted the three-dimensional positions of galaxies using their distances measured through redshift, a stunning pattern emerged. Galaxies were not randomly distributed at all. They were arranged along filaments and walls surrounding vast empty regions. One of the most famous early discoveries was the Bootes void, detected in 1981 by astronomer Robert Kirshner and his team. This spherical emptiness is about 330 million light-years across and contains only a few dozen galaxies, when it should contain thousands based on the average density of the universe. The discovery was shocking. How could such a vast region be so empty? What forces had cleared out so much space? The answer lies in how structure forms in the universe. It all goes back to the very beginning, to the moments just after the Big Bang. In that primordial fireball, matter was distributed almost perfectly uniformly throughout space. Almost, but not quite. Tiny quantum fluctuations, random variations in density that arose from the inherent uncertainty of quantum mechanics, meant that some regions were ever so slightly denser than others. These slight differences were the seeds of everything we see today. Over billions of years, gravity went to work. Regions that were slightly denser attracted more matter, growing denser still. Regions that were slightly less dense lost matter to their denser neighbors, becoming even emptier. This process is called gravitational instability, and it is responsible for the entire structure of the cosmic web. Think of it like water droplets on a window. Initially, the moisture is spread fairly evenly across the glass, but small irregularities in the surface cause some drops to merge and grow larger, while the spaces between them become drier. Given enough time, you end up with distinct streams of water separated by dry patches. The cosmic web formed in much the same way, just on a scale that dwarfs human comprehension. As matter flowed from underdense regions to overdense ones, the voids grew larger and emptier. The filaments and clusters grew more pronounced and dense. And this process continues today. The voids are still expanding, still emptying, still becoming more perfectly empty as the cosmic web evolves. Now here is where things take a dramatic turn. For most of the history of cosmology, voids were considered interesting, but relatively unimportant. They were the empty spaces between the real action. But recent discoveries have changed that view entirely. It turns out that one of these voids might be far more significant than anyone imagined, because we might be living inside one. In 2013, 3 astronomers named Ryan Keenan, Amy Barger, and Lennox Cowie published a study that would send ripples through the cosmology community. Using data from multiple galaxy surveys, they analyzed the distribution of matter around our local region of space. What they found was remarkable. The Milky Way galaxy, along with the local group of galaxies to which we belong, appears to sit near the center of an enormous underdensity, a region of space that has significantly less matter than the cosmic average. This underdensity stretches for about 2 billion light-years in diameter, making it one of the largest voids ever observed. It became known as the KBC Void, named after the initials of its discoverers. Others call it the local hole. To understand what this means, consider this. If you were to draw a sphere around our galaxy with a radius of about 1 billion light-years, the matter density inside that sphere would be roughly 20% lower than what you would find in a typical region of the universe. That might not sound like much, but on cosmic scales, it is a staggering difference. Evidence for the KBC Void has come from multiple independent observations. Astronomers have counted galaxies in different directions and at different distances from Earth. They have measured the density of gas and dust. They have analyzed patterns in the distribution of galaxy clusters. And across different wavelengths of light, from visible to infrared to X-ray, the same picture emerges. Our cosmic neighborhood is emptier than it should be. This is not the same as the smaller local void that astronomers have known about for decades. That void, discovered by Brent Tully and Rick Fisher in 1987, is a relatively nearby empty region that sits adjacent to our local group. The KBC Void is something much larger, a supervoid that encompasses not just our immediate neighborhood, but a significant chunk of what astronomers call the local universe. The implications of this discovery are profound. If we truly live inside a giant cosmic void, it could help explain one of the biggest mysteries in modern physics. A mystery that has been building for over a decade and shows no signs of going away. Scientists call it the Hubble tension, and understanding it requires us to dive into the nature of the universe's expansion itself. The universe is expanding. This is one of the most fundamental discoveries in the history of science. In 1929, astronomer Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This relationship, now called Hubble's law, revealed that space itself is stretching, carrying galaxies along for the ride like raisins in rising bread dough. The rate at which this expansion occurs is measured by something called the Hubble constant. This number tells us how fast a galaxy at a given distance is moving away from us due to the expansion of space. It is expressed in units of kilometers per second per megaparsec. A megaparsec is about 3.26 million light years, a standard unit astronomers use for cosmic distances. Measuring the Hubble constant accurately has been one of the great projects of modern astronomy. For decades, different methods gave different answers, and scientists assumed that better measurements would eventually converge on a single value. But something strange has happened. Instead of converging, the measurements have split into two camps, and the gap between them refuses to close. One way to measure the Hubble constant is to look at the early universe. The cosmic microwave background, often called the CMB, is the afterglow of the Big Bang. It is the oldest light we can see, released about 380,000 years after the universe began. By studying the patterns in this ancient light, scientists can figure out what the early universe looked like and use established physics to calculate what the expansion rate should be today. The European Space Agency's Planck satellite mapped the cosmic microwave background with extraordinary precision. Using that data and the standard model of cosmology, scientists calculated that the Hubble constant should be about 67 kilometers per second per megaparsec. This means a galaxy 1 megaparsec away should be receding from us at about 67 kilometers per second due to the expansion of space. But there is another way to measure the Hubble constant. Instead of looking at the early universe and predicting what should happen today, you can simply look at the universe today and measure what is actually happening. This involves observing certain types of stars and stellar explosions that have known luminosities, called standard candles. By comparing how bright these objects appear to how bright they actually are, astronomers can calculate their distances. Combined with measurements of how fast they are moving away from us, this gives a direct measurement of the expansion rate. The most precise of these local measurements come from a project called Shade0ES, led by Nobel laureate Adam Rees, using observations of Cepheid variable stars and type Ia supernovae. The SRH0ES team has consistently measured the Hubble constant at about 73 to 74 kilometers per second per megaparsec. That is significantly higher than the Planck prediction of 67. At first, scientists assumed this discrepancy would disappear as measurements improved. But the opposite has happened. Both sets of measurements have become more and more precise, and the gap between them has remained stubbornly persistent. The early universe says the expansion rate should be about 67. The local universe says it is actually about 73. The difference is about 8 to 9%, which may sound small, but is enormous in terms of measurement precision. This disagreement is the Hubble tension, and it is not just a minor puzzle. If it is real, if it cannot be explained by some hidden error in the measurements, then our fundamental understanding of the universe may be incomplete. The standard model of cosmology, which has successfully explained almost everything we have observed about the cosmos, might be missing something crucial. This is where the KBC Void enters the picture. Some scientists believe that living inside this giant underdensity could be skewing our local measurements of the Hubble constant, making the universe appear to expand faster in our neighborhood than it actually does on average. To understand why, we need to talk about gravity and its relationship to cosmic expansion. Gravity is the force that pulls matter together. When you drop something, it falls because the Earth's gravity is pulling it down. On cosmic scales, gravity is what causes galaxies to form, what holds clusters together, and what shapes the entire cosmic web. But gravity also affects how fast the universe expands. In regions with more matter, gravity works to slow down the expansion. Think of it like rolling a ball up a hill. The more mass you have pulling back on the ball, the slower it goes. In contrast, in regions with less matter, there is less gravitational drag, and expansion proceeds more freely. Now imagine you are inside a cosmic void, a region with significantly less matter than average. The gravitational pull from the surrounding denser regions would be stronger than the pull from within the void. This creates an outward tug on everything inside the void, as matter gets drawn toward the denser walls surrounding the emptiness. Galaxies inside a void experience what is called an outflow. a bulk motion away from the void's center and toward the surrounding cosmic web. This outflow adds to the apparent recession velocity of galaxies. When we measure how fast nearby galaxies are moving away from us, we are measuring not just the cosmological expansion, but also any additional motion caused by local gravitational effects. If we are inside a void, this additional outward motion would make it look like the universe is expanding faster than it actually is. Astrophysicist Indranil Banik, one of the leading researchers on this topic, has calculated that the KBC void could cause the locally measured Hubble constant to be about 11% higher than the true global average. That is almost exactly the size of the Hubble tension. If this explanation is correct, then the Planck measurement of 67 would represent the true expansion rate of the universe, while the higher local measurements would be contaminated by our peculiar location inside an underdense region. This is a tantalizing possibility. It would resolve one of the biggest headaches in modern cosmology without requiring any new physics. The standard model would remain intact. We would just need to accept that our view of the universe is biased by our unusual cosmic address. But as with everything in science, the story is more complicated. Not everyone is convinced that the KBC void is large enough or empty enough to fully explain the Hubble tension. Some researchers point out that the surveys used to detect the void do not cover the entire sky and may be missing important information. Others argue that the density contrast, the difference between the void's density and the cosmic average, is not quite large enough to account for the full discrepancy. There is also a deeper philosophical issue at play. The standard model of cosmology is built on something called the cosmological principle. This principle states that, on sufficiently large scales, the universe looks the same in all directions and from all locations. It is homogeneous and isotropic. The existence of a structure as large as the KBC void, with us sitting near its center, challenges this principle. If the local universe is significantly different from the cosmic average out to distances of 1 billion light-years, then perhaps the universe is not as uniform as we have assumed. This is where the void story intersects with a much larger mystery, one that touches on the very fabric of reality. To understand what is truly breaking the universe, we need to explore the most enigmatic force in all of physics, a force that makes up nearly 70% of everything that exists, yet remains almost completely unexplained. We need to talk about dark energy. Dark energy is the name scientists give to whatever is causing the universe's expansion to accelerate. Yes, you read that correctly. The universe is not just expanding. It is expanding faster and faster with each passing moment. This discovery, made in 1998, earned its discoverers the Nobel Prize and completely upended our understanding of cosmic evolution. For most of its history, the universe's expansion was slowing down. This makes intuitive sense. After the initial push of the Big Bang, gravity should have been pulling everything back together, gradually decelerating the outward rush. And indeed, for the first 9 billion years or so, that is exactly what happened. But then something changed. About 5 billion years ago, the expansion stopped slowing and started speeding up. The culprit, as best as scientists can tell, is dark energy. This mysterious substance, or force, or property of space itself, works in the opposite direction from gravity. While gravity pulls matter together, dark energy pushes space apart. And unlike matter, which gets diluted as space expands, dark energy seems to maintain a constant density. As the universe grows larger, there is more space and therefore more dark energy, which drives even faster expansion. The leading candidate for dark energy is something called the cosmological constant. This is a term that Albert Einstein originally introduced into his equations of general relativity in 1917. At the time, Einstein believed the universe was static, neither expanding nor contracting, but his equations naturally predicted that the universe should be dynamic. To fix this, he added a constant term that would counterbalance gravity and keep things still. When Edwin Hubble discovered the expansion of the universe in 1929, Einstein reportedly called the cosmological constant his greatest blunder. He had missed the chance to predict one of the most important discoveries in cosmology. But decades later, the cosmological constant made a comeback. In the modern interpretation, it represents the energy of empty space itself, a kind of quantum fizzing that permeates all of reality. Here is where the void story becomes even more intriguing. Dark energy and cosmic voids interact in fascinating ways. Remember that voids are regions with less matter than average. This means they have less gravitational drag working against expansion. In these empty regions, dark energy's repulsive effect faces less opposition, allowing expansion to proceed more quickly. Think of it this way. In a dense region full of galaxies and dark matter, gravity is working hard to pull everything together. Dark energy is pushing outward, but it has to fight against this gravitational resistance. The expansion in such regions is slower than average. Now, consider a void. With little matter to provide gravitational resistance, dark energy has almost free rein. The expansion proceeds faster than in denser regions. This difference in expansion rates creates a complex picture of cosmic evolution. The voids grow larger and emptier as their faster expansion stretches the space within them. The dense regions become relatively denser as matter continues to accumulate along filaments and in clusters. Over billions of years, the contrast between these regions becomes more pronounced. Now consider what happens if you live inside one of these voids, as we apparently do. Not only are you seeing the universe from an underdense region, but that region is also experiencing accelerated expansion due to the reduced gravitational opposition to dark energy. This could compound the effect that makes our local measurements of the Hubble constant appear higher than the true cosmic average. Some theorists have gone even further. They suggest that the KBC Void is not just a simple underdensity, but a kind of amplifier for dark energy's effects. In their models, the combination of the void's emptiness and dark energy's relentless push creates a localized bubble where the rules appear different from elsewhere in the cosmos. We are not just in an empty region. We are in a region where the fundamental dynamics of cosmic expansion are operating at a different pace. This idea is both exciting and troubling. Exciting because it might explain the Hubble tension without requiring exotic new physics. Troubling because it suggests that our view of the universe might be fundamentally biased. If we are sitting in a special location, then the measurements we make may not be representative of the cosmos as a whole. Everything we think we know about cosmic expansion, dark energy, and the fate of the universe might need to be reconsidered. The physics of emptiness is stranger than it might seem at first. When we think of empty space, we imagine nothingness, a pure vacuum devoid of any content. But modern physics tells us that empty space is anything but empty. Even in the most perfect vacuum imaginable, space itself has properties. It has energy, it fluctuates, and these properties have real measurable consequences. In quantum mechanics, empty space is a seething foam of virtual particles. Pairs of particles and antiparticles constantly pop into existence and annihilate each other, existing for just a fleeting moment before returning to nothingness. This quantum activity gives the vacuum an inherent energy called zero-point energy or vacuum energy. And according to some theories, this vacuum energy is what we experience as dark energy. Here is the catch, and it is a major one. When physicists calculate how much vacuum energy there should be based on quantum theory, they get an answer that is absurdly, impossibly large. The predicted value is off by about 120 orders of magnitude from what we actually observe. That is not a 10% error. That is a number so wrong that it has been called the worst prediction in the history of physics. This discrepancy is known as the cosmological constant problem, and it remains unsolved. Somehow, the vacuum energy of space is almost perfectly cancelled out by some unknown mechanism, leaving just a tiny residual that we call dark energy. Understanding why this cancellation occurs is one of the greatest challenges in theoretical physics. Now consider how this puzzle intersects with cosmic voids. In a void, there is less matter to contribute to the local energy density. The vacuum energy of empty space becomes the dominant factor. Whatever dark energy is, its effects are most pronounced in these empty regions. By studying voids, scientists hope to learn more about the nature of dark energy itself. Some researchers have proposed that dark energy might not be constant at all. Instead, it could vary in strength from place to place or change over time. This hypothetical evolving dark energy is sometimes called quintessence. If dark energy is stronger in voids than in dense regions, it could help explain why our local universe appears to be expanding faster than expected. Recent observations from the Dark Energy Spectroscopic Instrument, or DESI, have added fuel to this speculation. By mapping the positions of millions of galaxies and tracing the history of cosmic expansion, DESI has found tentative evidence that dark energy might be changing over time. If confirmed, this would be a revolutionary discovery, overturning the simple cosmological constant model and opening the door to new physics. But whether dark energy is constant or evolving, its interplay with cosmic voids is crucial for understanding the expansion of the universe. The voids are not just empty spaces. They are laboratories where the fundamental forces shaping the cosmos are most clearly revealed. Let us dive deeper into what happens to space-time inside a cosmic void. According to Einstein's general theory of relativity, mass and energy tell space how to curve, and curved space tells matter how to move. This elegant relationship is the foundation of our understanding of gravity on cosmic scales. When there is a lot of mass in a region, space-time curves significantly, creating the gravitational wells that hold galaxies together and cause light to bend as it passes near massive objects. Inside a void, the situation is different. With little mass to curve space-time, the geometry is flatter. Light travels straighter paths. The gravitational wells are shallower and more widely spaced. It is like comparing a mountainous landscape to a gentle plain. In the mountains, water collects in valleys and rivers carved through rock. On the plain, water spreads more evenly and flows more freely. This flatness affects how objects move through the void. Without significant gravitational obstacles, galaxies inside voids tend to drift outward, pulled toward it, the denser walls surrounding the empty region. This outflow creates a kind of cosmic current, a systematic motion that carries galaxies away from the void center. Our own Milky Way is part of this flow, being tugged not just by the expansion of the universe, but by the gravitational imbalance of living in an underdense region. Scientists have measured this motion. The local sheet, a flattened array of galaxies that includes the Milky Way, is rushing away from the center of the local void at about 260 kilometers per second. that is nearly 600,000 miles per hour. Even more dramatically, when you account for all the gravitational influences on our galaxy, including the pull from distant clusters and the push from nearby voids, the Milky Way is hurtling through space at nearly 1 million kilometers per hour relative to the cosmic microwave background. These velocities are mind-boggling, but you do not feel them. Just as you do not feel the Earth's rotation or its orbit around the Sun, you are oblivious to the cosmic journey that carries you through the universe. Yet these motions are real, and they matter for understanding how the cosmos evolves. Now let us zoom out even further and consider the history of cosmic voids. Where did they come from? How did such vast emptiness arise in a universe that began as a nearly uniform soup of matter and energy? The story begins, as all cosmic stories do, with the Big Bang. In the first fraction of a second of existence, the universe underwent a period of incredibly rapid expansion called inflation. During inflation, space expanded faster than the speed of light, stretching quantum fluctuations to cosmic scales. These fluctuations, originally tiny variations in energy density at the quantum level, became the seeds of all structure in the universe. When inflation ended, the universe was left with a pattern of slightly denser and slightly less dense regions imprinted across the cosmos. The differences were tiny, variations of only about 1 part in 100,000 from the average density. But that was enough. Gravity took over, amplifying these differences over billions of years. The slightly denser regions attracted more matter from their surroundings. They grew denser still, eventually collapsing to form the first stars, galaxies, and clusters. The slightly less dense regions lost matter to their denser neighbors. They became emptier and emptier, expanding faster than the cosmic average because there was less gravitational drag to slow them down. This process of gravitational instability created a kind of cosmic sorting mechanism. Matter flowed from underdense regions to overdense ones, like water flowing downhill. The cosmic web emerged with dense filaments and clusters connected by walls, all surrounding ever-expanding voids. But the story does not end there. Once voids form, they do not stay static. They continue to evolve, growing larger and emptier over cosmic time. The expansion of the universe stretches the voids, while the matter along their edges continues to flow outward into the surrounding dense regions. It is as if the voids are inflating like balloons, pushing their walls farther and farther apart. This evolution has been beautifully captured in computer simulations. Projects like the Millennium Simulation and Illustrise TNG have modeled the growth of cosmic structure from the early universe to the present day. In these simulations, you can watch voids form from the initial density fluctuations, grow larger as time passes, and occasionally merge with each other to form even larger empty regions. The simulations show that voids are not perfectly spherical. Instead, they tend to be somewhat irregular, bounded by the twisted geometry of the surrounding cosmic web. Some voids are shaped like giant eggs, others are more like flattened discs, and as they grow, their shapes continue to change, molded by the gravitational pulls of the structures around them. Over very long timescales, something remarkable happens. The voids begin to dominate the universe's volume. Even though most of the matter is concentrated in the cosmic web, most of the space is inside voids. Current estimates suggest that voids already make up more than 70% of the universe's volume, and this fraction is growing. If we extrapolate into the far future, a picture emerges of a universe that will become increasingly dominated by emptiness. The filaments will stretch and thin. The clusters will move farther apart. and the voids will expand until they fill almost everything. In a sense, the universe is destined to become one vast void, a nearly empty expanse punctuated by isolated islands of matter. This is not just theoretical speculation. It is the logical consequence of dark energy's relentless push. As dark energy continues to drive cosmic expansion faster and faster, everything in the universe will be carried farther and farther apart. The cosmic web will stretch until it tears. The connections between galaxies will be severed. And eventually, each galaxy will find itself alone in an otherwise empty universe. But that is the fate of the cosmos in general. What about our specific corner of it? What does living inside the KBC Void mean for our galaxy and our cosmic neighborhood? The local group of galaxies, which includes the Milky Way, the Andromeda Galaxy, and a few dozen smaller companions, is gravitationally bound. This means that the expansion of the universe will not tear us apart from our nearest neighbors. In fact, the Milky Way and Andromeda are heading toward each other and will merge in about 4 to 5 billion years, forming a new supergalaxy sometimes called Milkdromeda. But beyond our immediate neighborhood, the picture is different. Galaxies that are not gravitationally bound to us will continue to recede as space expands. And because we live in an underdense void, this recession is happening faster than it would in a denser region. The galaxies we can see today are moving away from us at an accelerated rate, their light stretching toward the red end of the spectrum as the space between us grows. Over billions of years, this accelerated expansion will have profound consequences. Galaxies that are currently visible will eventually cross a kind of cosmic horizon and disappear from view. Not because they have gone anywhere, but because the space between us will be expanding so fast that their light can never reach us. They will be carried beyond the edge of our observable universe, lost to us forever. This phenomenon is sometimes called cosmic isolation. In the far future, the universe will seem emptier and emptier from any given vantage point. Not because matter is disappearing, but because the vast distances created by expansion will make most of the cosmos invisible. Astronomers of the distant future, if there are any, may look out at a sky containing only their own galaxy or galaxy group, unaware that trillions of other galaxies exist beyond the unreachable horizon. And here is the thing: if the KBC Void is real, and if it is affecting our local expansion rate, this isolation may come sooner for us than for observers in denser regions. We are already in a relatively empty neighborhood. The walls of our void are being pushed farther away by the differential expansion. The cosmic web that connects us to the rest of the universe is being stretched and thinned. We are, in a sense, becoming increasingly isolated from the broader cosmos. This brings us to one of the deepest questions raised by the void hypothesis. If our measurements of the universe are being distorted by our location inside a void, how do we know what the true nature of the cosmos really is? How can we trust our observations if they are biased by our peculiar position? This is not just a philosophical puzzle. It has practical implications for how we do cosmology. Many of the techniques astronomers use to study the universe assume that our local environment is representative of the cosmos as a whole. If that assumption is wrong, our conclusions might be systematically off. Consider the measurements of the Hubble constant. As we discussed, local measurements using standard candles give a higher value than predictions based on the early universe. If the KBC Void explanation is correct, then the local measurements are contaminated by our unusual location. The true expansion rate of the universe would be closer to what the early universe data predict, around 67 kilometers per second per megaparsec. But this raises another question. If our local universe is not representative, what else might we be getting wrong? Are our measurements of dark energy's properties biased? What about our counts of galaxy clusters or our measurements of the cosmic microwave background? Could our entire picture of the cosmos be skewed by the accident of our location? These questions do not have easy answers. Some researchers believe that the KBC Void, while real, is not large enough or empty enough to cause major problems for cosmology. They argue that most of our measurements are robust and that the Hubble tension likely has some other explanation, perhaps new physics or subtle systematic errors in the observations. Others are more cautious. They point out that the cosmological principle, the assumption of cosmic homogeneity, has never been directly tested on the largest scales. We assume the universe is uniform because our theories require it, and because observations so far have been consistent with it. But the existence of the KBC Void suggests that inhomogeneities on billion light-year scales may be more common than we thought. This debate gets at the heart of how we do science at the edge of knowledge. When you are studying something as vast and remote as the cosmos, you cannot run controlled experiments. You cannot travel to another galaxy to get a second opinion. All you can do is observe from your one vantage point and try to infer the nature of the whole from the limited sample you can access. The KBC Void reminds us that our vantage point may not be typical. We could be living in a cosmic outlier, a region that does not represent the average conditions of the universe. And if that is true, our picture of the cosmos might be more local and less universal than we have assumed. Let us now turn to the broader implications of cosmic voids for the fate of the universe. We have already mentioned that voids are growing and will eventually dominate cosmic volume. But there is more to the story than just empty space getting emptier. The interplay between voids and dark energy is shaping the ultimate destiny of everything that exists. As dark energy continues to drive accelerated expansion, the universe is evolving toward a state that physicists call heat death, or the big freeze. This is a condition where all energy is spread so thinly and uniformly that nothing interesting can happen anymore. No stars can form. No chemistry can occur. Everything fades into a cold, dark, empty stillness. Voids are in some sense previewing this fate. They are the regions where matter is already sparse, where the density is approaching the vacuum state that the entire universe will eventually reach. By studying voids, scientists can get a glimpse of what the far future cosmos will look like. But there are other possibilities too. Some theorists have proposed that dark energy might not behave the same way forever. If dark energy's strength increases over time, it could eventually overcome not just cosmic expansion, but the forces holding matter together. Galaxies would be torn apart, then stars, then planets, then atoms. This catastrophic scenario is called the Big Rip. The universe would literally rip itself to pieces in a finite time, perhaps 20 billion years from now if some models are correct. In a Big Rip scenario, voids would play a dramatic role. They would be the regions where the ripping begins, where the accelerated expansion first becomes strong enough to overcome local gravity. The universe would not end all at once, but would unravel from the voids outward, with the destruction spreading from the emptiest regions into the denser ones. This is speculative, of course. Current observations suggest that dark energy is probably constant, not increasing over time. The Big Freeze is more likely than the Big Rip, but the fact that we are uncertain about dark energy's nature means we cannot rule out more dramatic outcomes. The void we live in could be a preview of paradise or purgatory, depending on how cosmic evolution unfolds. Even in the more sedate Big Freeze scenario, the void has implications for the long-term future of intelligence in the universe. If civilizations exist in the far future, they will face increasing isolation as the expansion accelerates. Communication between galaxies will become impossible. Travel between them will be out of the question. Each galaxy group will be an island universe, cut off from all others by the vast and growing gulf of empty space. Some futurists have speculated about how advanced civilizations might cope with this isolation. Perhaps they could migrate to denser regions of the cosmic web, where the local expansion is slower and the neighbors are closer. Perhaps they could harvest energy from the vacuum itself, tapping into the dark energy that permeates all of space. Or perhaps they would simply accept their fate, making peace with a cosmos that is fundamentally destined for loneliness. These speculations may seem far removed from the practical concerns of present-day astronomy, but they illustrate why understanding cosmic voids matters. The emptiness between galaxies is not just dead space. It is an active player in cosmic evolution, shaping the structure, dynamics, and ultimate fate of everything that exists. Let us return to the specific puzzle of the KBC Void and the Hubble tension. We have discussed how living inside an underdense region could make the universe appear to expand faster locally. But is this explanation actually correct? What is the current state of scientific opinion? The honest answer is that we do not know for sure. The void hypothesis is one of several competing explanations for the Hubble tension. Others include systematic errors in the measurements, new physics beyond the standard model, or some combination of factors. Some recent studies have provided support for the void hypothesis. Measurements of galaxy bulk flows, the systematic motions of galaxies through space, show that matter in our region is indeed flowing outward faster than expected. This is consistent with what you would see if we were inside a large void. The velocities and directions of these flows match reasonably well with predictions from void models. Other observations are more ambiguous. The cosmic microwave background, for instance, looks remarkably uniform across the sky. If we were inside a very large void, we might expect to see some signature of that void imprinted on the CMB. Some researchers claim to have found such signatures. Others argue that the data is consistent with no void at all. The James Webb Space Telescope has recently provided new data that bears on this question. Webb's observations of distant galaxies and supernovae have confirmed that the Hubble measurements from the Hubble Space Telescope are accurate. This rules out certain types of systematic errors that skeptics had proposed, but it does not directly test the void hypothesis. The question of whether our location biases our measurements remains open. New surveys are underway that could help settle the debate. The Dark Energy Spectroscopic Instrument is mapping the three-dimensional positions of tens of millions of galaxies, creating the most detailed map of the cosmic web ever made. By carefully measuring how matter is distributed around us, DESI could determine whether the KBC void is real, and if so, how it affects our measurements of cosmic expansion. Other projects, like the Euclid Space Telescope and the upcoming Vera Rubin Observatory, will add to this effort. They will survey billions of galaxies across vast swaths of sky, looking for patterns that reveal the true structure of the universe. Within the next decade, we should have a much clearer picture of whether we live in a void and what that means for cosmology. In the meantime, scientists continue to debate and speculate. Some believe the Hubble tension will be resolved with better data, without requiring any revision to our standard model. Others think it is the first crack in the edifice, the beginning of a revolution in our understanding of the cosmos. What is clear is that the question matters. The expansion of the universe is not just an abstract curiosity. It determines the past, present, and future of everything that exists. Getting the Hubble constant right is essential for understanding where we came from, where we are, and where we are going. And if the void hypothesis is correct, it would have a profound lesson to teach us. It would remind us that our view of the cosmos is not neutral. We see the universe from a specific place at a specific time, and that perspective shapes what we observe. The dream of a purely objective cosmology, uncontaminated by local peculiarities, might be impossible to achieve. This is not a failure of science. It is a fact about the nature of observation. Every measurement is made from somewhere by someone, using tools that have their own characteristics and limitations. The best we can do is be aware of these biases and try to account for them. The KBC Void, if it exists, is simply one more factor to consider in our quest to understand the cosmos. There is another way to think about the significance of cosmic voids that brings the science down to a more personal level. Consider what it means to look up at the night sky and know that you are inside one of the emptiest regions of the cosmos. When you gaze at the stars on a clear night, you see the local neighborhood of our galaxy. The bright points of light are mostly suns within a few hundred or few thousand light years of Earth. Beyond them, in the hazy band of the Milky Way, are billions more stars, the combined glow of our galactic home. And beyond that, invisible to the naked eye but detectable with telescopes, are countless other galaxies stretching to the edge of the observable universe. But the space between those galaxies is not uniform. In some directions, galaxies cluster thickly along filaments and walls. In others, they thin out into the vast emptiness of voids. And according to the best current evidence, we happen to be positioned in one of those empty directions, at least on the largest scales. This is not obvious from casual observation. The immediate neighborhood of the Milky Way is actually fairly busy. The local group contains more than 80 galaxies, including the giant spiral Andromeda and the fuzzy blobs of the large and small Magellanic Clouds visible from the southern hemisphere. Beyond the local group, we are part of the Virgo supercluster, a vast collection of galaxy groups and clusters centered on the Virgo cluster about 50 million light-years away. The Virgo supercluster is itself part of an even larger structure called Laniakea, a term from Hawaiian meaning immense heaven. Laniakea spans about 500 million light-years and contains roughly 100,000 galaxies, all slowly flowing toward a gravitational center called the Great Attractor. So at scales of hundreds of millions of light-years, our cosmic neighborhood is actually quite rich. It is only when you zoom out further, to scales of 1 billion light-years and beyond, that the emptiness becomes apparent. The KBC Void encompasses not just the local group or the Virgo supercluster, but a significant portion of Laniakea and the regions beyond. We are inside a bubble of relative emptiness that stretches in all directions for nearly 1 billion light-years. This has implications for what we can see and measure. When astronomers conduct surveys of distant galaxies, they are looking through this bubble of emptiness. The galaxies they observe are either inside the void, in which case they might share our peculiar gravitational environment, or outside it, in which case their light has traversed the void to reach us. This geometry affects the measurements in subtle ways. Light traveling through a void experiences different gravitational effects than light traveling through denser regions. There is less gravitational lensing, less absorption by intergalactic gas, and different redshift patterns due to the peculiar velocities of galaxies flowing out of the void. Accounting for all these effects is challenging, and it is part of why the debate over the KBC Void and the Hubble tension remains unresolved. Let us explore some of the specific observations that have shaped our understanding of the local void and its possible impact on cosmology. One crucial line of evidence comes from galaxy counts. By tallying how many galaxies exist at different distances and in different directions, astronomers can map the density of the universe around us. These surveys have consistently shown that the number of galaxies per unit volume is lower in our immediate neighborhood than in more distant regions. The surveys span multiple wavelengths of light. Optical surveys count galaxies based on their visible starlight. Infrared surveys penetrate dust clouds to find galaxies that would otherwise be hidden. X-ray surveys detect the hot gas in galaxy clusters. Radio surveys map the distribution of gas and active galactic nuclei. Despite using different techniques and different instruments, these surveys agree that the local universe is underdense. One particularly important study was conducted by the 2-micron all-sky survey, or 2MASS. This infrared survey mapped the distribution of galaxies across the entire sky, avoiding the obscuring effects of dust in our own galaxy. The resulting map clearly shows the filamentary structure of the cosmic web, with dense clusters connected by threads of galaxies. It also shows that our local region is relatively sparse compared to the cosmic average. Another key observation involves measuring the cosmic microwave background through different regions of the sky. The CMB is the afterglow of the Big Bang, released about 380,000 years after the universe began. By the time this ancient light reaches us, it has traveled through billions of light years of space, interacting with the matter it encounters along the way. When CMB photons pass through a void, something interesting happens. Because the void is expanding faster than its surroundings, the photons lose a tiny bit of energy as they cross it. This effect, called the integrated Sachs-Wolf effect, leaves a slight cold spot in the CMB in the direction of a void. Conversely, CMB photons passing through dense clusters gain energy and leave a warm spot. Astronomers have searched for such cold spots in the direction of known voids. One of the most famous is the cold spot, a region in the constellation Eridanus, where the CMB temperature is slightly lower than average. Some researchers have proposed that this cold spot could be caused by a supervoid along that line of sight, possibly even connected to or part of the KBC Void. Others argue that the cold spot is a statistical fluke, not evidence of any particular structure. The debate continues, with new data from surveys like the Dark Energy Survey providing more detailed maps of the matter distribution in the cold spot direction. If a large void is confirmed there, it would add to the evidence that the local universe is characterized by unusually large empty regions. A different type of evidence comes from measuring the velocities of galaxies. As we discussed, galaxies inside a void experience an outward flow toward the surrounding denser regions. By measuring how fast galaxies are moving and in what directions, astronomers can infer the gravitational forces acting on them, and therefore the distribution of matter around them. The Cosmic Flows project has been assembling the largest database of galaxy velocities ever compiled. By analyzing data from thousands of galaxies, the project has mapped the bulk flow of matter in our cosmic neighborhood. The results show that galaxies are indeed flowing outward from underdense regions and toward overdense ones, consistent with the void model. Interestingly, some of these bulk flows are larger than what the standard model of cosmology predicts. If, The matter distribution were perfectly smooth on large scales, as the cosmological principle suggests, the flows should be relatively modest. But the observed flows are faster and extend over larger distances than expected. This could be evidence that structures like the KBC Void are real and are having a significant gravitational impact on their surroundings. The discrepancy between observed and predicted bulk flows is another tension in cosmology, sometimes called the sigma-8 tension, after the statistical parameter used to describe matter clustering. Like the Hubble tension, it suggests that something might be off with our standard model. And like the Hubble tension, it could potentially be explained if the local universe is less homogeneous than we have assumed. Let us now consider the theoretical side of the puzzle. How do physicists model the effects of cosmic voids on the expansion of the universe? The standard model of cosmology, known as lambda CDM, is built on the assumption that the universe is homogeneous and isotropic on large scales. This means that if you average over big enough volumes, the density of matter and the rate of expansion should be the same everywhere. Local variations exist, of course, but they are supposed to cancel out when you look at the big picture. This assumption is encoded in the mathematical framework of cosmology, specifically in the Friedmann equations that describe how the universe expands. These equations are derived from Einstein's general theory of relativity under the assumption of a perfectly uniform cosmos. They have been remarkably successful in explaining observations, from the cosmic microwave background to the distribution of galaxies, to the abundances of light elements formed in the Big Bang. But what if the assumption of homogeneity is wrong? What if the universe is lumpier than we thought, with large underdense and overdense regions that do not average out to uniformity? This question has led to a field of research called inhomogeneous cosmology. Researchers in this field develop mathematical models that relax the assumption of perfect homogeneity and explore how variations in density affect cosmic expansion. One key finding is that in an inhomogeneous universe, the expansion rate is not a single number that applies everywhere. Instead, it varies from place to place, being faster in voids and slower in dense regions. When you measure the expansion rate, the value you get depends on where you are and what you are measuring. This has led to the concept of the effective Hubble constant, which is the expansion rate that an observer in a particular location would measure. If you are inside a void, your effective Hubble constant would be higher than the global average. If you are inside a cluster, it would be lower. The true cosmic expansion rate, the one that describes the universe as a whole, might be different from any locally measured value. Calculating the effective Hubble constant for an observer inside a void like the KBC is a complex task. It requires detailed models of how the void affects light propagation, galaxy motions, and the apparent brightness and redshift of distant objects. Different researchers using different techniques have obtained somewhat different answers, which is part of why the debate continues. But the basic idea is robust. Living inside a void will bias your measurements of the expansion rate. The only question is how much. Some researchers have gone further and proposed that the entire apparent acceleration of the universe might be an illusion caused by our location in a void. In this view, dark energy does not exist at all. The universe is not accelerating on a global scale. We just think it is because we are observing from an underdense region, where the local expansion is faster than average. This is a radical idea, and most cosmologists are skeptical. The evidence for cosmic acceleration comes from multiple independent sources, including supernovae, the cosmic microwave background, and the distribution of galaxies. It would be surprising if all these observations could be explained by a single local effect. Moreover, the apparent acceleration began relatively recently in cosmic history, about 5 billion years ago. This timing is hard to explain with a simple void model, which would predict a more gradual effect. The transition from deceleration to acceleration that we observe seems to require something beyond just inhomogeneous matter distribution. Still, the void skeptics make an important point. Our standard model assumes a level of uniformity that may not be justified. Even if dark energy is real, its effects may be modified by the local structure of the cosmos in ways we do not fully understand. The interplay between dark energy and inhomogeneity is an active area of research. Let us step back and consider the big picture. The universe that modern cosmology describes is a strange place. It began in a hot, dense state and has been expanding and cooling ever since. Most of it is made of dark matter and dark energy, mysterious substances whose nature we do not understand. It is structured as a cosmic web of filaments and voids, with galaxies clustered along the threads and emptiness in between. And somewhere in this vast web, on a small rocky planet orbiting an ordinary star in an undistinguished galaxy, beings have evolved who can look up at the sky and wonder what it all means. We have built telescopes that can see almost to the beginning of time. We have developed theories that explain the evolution of the cosmos from its first moments to its far future. And yet, we are still struggling with basic questions about how fast the universe is expanding and what is causing that expansion. The KBC Void is one piece of this puzzle. It may be a major piece, explaining the Hubble tension and teaching us that our cosmic address matters more than we thought. Or it may be a minor distraction, a local peculiarity that has little bearing on the big questions. Either way, it is a reminder that the universe is more complex and surprising than our simple models can capture. There is poetry in the idea that we live in a void. Humans have always felt small and insignificant compared to the vastness of the cosmos. But there is something especially poignant about realizing that even among the stars and galaxies, we inhabit an empty place. Not quite the center of the universe, as ancient astronomers imagined, but close to the center of a great nothingness. This nothingness is not truly empty, of course. Space itself has properties and energy. Quantum fields fluctuate even in the vacuum. Dark energy permeates every cubic centimeter of existence. But in terms of galaxies and stars and planets and life, voids are the loneliest places in the cosmos. And we are, it seems, among the lonely ones. Perhaps this is appropriate. Life and intelligence are rare enough in the universe as far as we know. Most of the cosmos is hostile to creatures like us, too hot or too cold or too empty to support complex chemistry and biological evolution. We exist in a narrow habitable zone around our star, on a single planet in a vast galaxy, in a relatively sparse region of an inconceivably enormous universe. The void that surrounds us is just one more reminder of how improbable and precious our existence really is. Now let us turn to the practical implications of the void hypothesis for the future of cosmological research. If we truly live inside a giant cosmic void, how should that change how we do astronomy? One obvious answer is that we need better maps. The existing surveys that have detected the KBC void cover limited portions of the sky and have significant uncertainties. To really nail down the size, shape, and density profile of the void, we need more comprehensive data. This is where upcoming surveys like those from DESI, Euclid, and the Vera Rubin Observatory come in. These projects will observe billions of galaxies across huge swaths of sky, measuring both their positions and their velocities. By combining these measurements, astronomers can reconstruct the three-dimensional distribution of matter to unprecedented precision. DESI, the dark energy spectroscopic instrument, is particularly relevant because of its focus on measuring cosmic expansion. By tracking patterns in the galaxy distribution called baryon acoustic oscillations, DESI can trace the expansion history of the universe with exquisite accuracy. If the local expansion rate is being affected by a void, DESI should be able to detect the signature. Euclid, a European Space Agency mission launched in 2023, is surveying the sky in visible and infrared light to study the distribution of dark matter and dark energy. Its wide field of view allows it to map vast areas efficiently, building up a picture of cosmic structure on the largest scales. Euclid data will help determine whether the KBC Void is a real feature or a statistical fluctuation. The Vera Rubin Observatory, under construction in Chile, will conduct a decade-long survey of the southern sky, imaging billions of galaxies and discovering millions of supernovae. This torrent of data will enable new tests of cosmological models and potentially reveal structures that previous surveys have missed. Beyond better maps, we also need better theoretical models. The tools cosmologists use to interpret observations are based on assumptions of a homogeneity that may not hold. Developing frameworks that can handle realistic levels of cosmic structure is a major challenge. Some progress has been made. Numerical simulations can now model the growth of cosmic structure with impressive detail, including the formation and evolution of voids. By comparing simulated voids to real ones, researchers can test whether the standard model produces the right kinds of structures or whether something is missing. Other approaches use analytical techniques to derive approximate formulas for how voids affect observables. These formulas can then be applied to real data to estimate the size of the effect. While less precise than full simulations, analytical approaches are faster and can provide useful intuition. A third avenue involves using machine learning to extract patterns from large datasets. Neural networks can be trained to recognize the signatures of voids in galaxy surveys, potentially finding subtle effects that traditional methods would miss. This is a young field, but early results are promising. Whatever techniques are used, the goal is the same. We need to figure out whether the KBC Void is real, how big and empty it is, and what impact it has on our measurements of the cosmos. Only then can we be confident that our picture of the universe is accurate. There is another practical consideration worth mentioning. If the void hypothesis is correct and local measurements are biased, it would have implications for cosmological parameter estimation. Cosmological parameters are the numbers that describe the universe. They include the Hubble constant, the densities of dark matter and dark energy, the amplitude of primordial fluctuations, and several others. By fitting models to observations, cosmologists estimate these parameters and their uncertainties. But what if different observations are affected differently by our location in a void? Measurements of distant objects might be biased one way, while measurements of nearby objects are biased another. The resulting parameter estimates could be inconsistent, leading to apparent tensions like the Hubble tension. Resolving these tensions requires carefully accounting for the effects of cosmic structure. This means not just measuring the parameters, but understanding the systematic errors introduced by our peculiar vantage point. It is a challenging task, but it is essential for precision cosmology. Let us now explore what the future might look like if the universe continues on its current trajectory. We have discussed how voids are growing and dark energy is driving accelerated expansion. What does this mean for the long-term fate of the cosmos? The standard prediction is the Big Freeze, also known as heat death. In this scenario, the universe continues expanding forever, getting colder and emptier with each passing eon. Stars eventually burn out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies merge and then drift apart, isolated by the ever-growing gulf of expanding space. Over truly enormous timescales, even black holes evaporate through a quantum process called Hawking radiation. The matter that remains slowly decays as protons and other particles gradually break apart. Eventually, the universe reaches a state of maximum entropy, a cold, dark, diffuse sea of particles, with no structure, no energy gradients, and no possibility for change. This is not a sudden catastrophe, but an incremental winding down. The process would take unimaginable lengths of time, far longer than the current age of the universe. But the direction is clear. The cosmos is heading toward a final stillness from which there is no return. Voids play a starring role in this scenario. They are the regions where the final state is most advanced. With less matter to cluster and burn, voids are already approaching the conditions of the far future. They are previews of the cosmic endgame, windows into the emptiness that awaits. If we could somehow visit a truly empty void, one with no galaxies at all, we would see something very close to the final state of the universe. A vast dark expanse with nothing but the faint glow of the cosmic microwave background, slowly fading toward absolute zero. It would be the loneliest place imaginable, a glimpse of eternity. But there is hope in this darkness, at least for the foreseeable future. The timescales for heat death are so vast that countless generations of stars and possibly civilizations could flourish before the end. The universe has billions of years of stellar activity ahead of it, plenty of time for life and intelligence to explore and understand the cosmos. And within the voids themselves, there is still activity. Even the emptiest void is not perfectly empty. Dwarf galaxies drift through the darkness. Gas slowly falls into halos of dark matter. Rare stars occasionally form and briefly illuminate the void with their light. Life might even find niches in these sparse environments, adapting to conditions very different from our own. The KBC Void, our cosmic home, is not so empty that life is impossible here. Obviously, we exist, along with hundreds of billions of other stars in our galaxy and trillions of galaxies in our observable universe. The underdensity is subtle, noticeable only on the largest scales. Locally, in the solar system, and even within the Milky Way, conditions are quite normal. But the void does affect how we see the rest of the cosmos. It shapes our perception of cosmic expansion, our measurements of dark energy, and our understanding of the universe's past and future. We are not just observers of the cosmos. We are participants in it, embedded in its structure and constrained by our location. This brings us to perhaps the most profound aspect of the void story. The realization that our view of the universe is shaped by where we happen to be is more than just a technical complication for astronomers. It is a philosophical lesson about the nature of knowledge and our place in the cosmos. Throughout human history, we have progressively removed ourselves from the center of creation. The Earth is not the center of the solar system. The Sun is not the center of the galaxy. Our galaxy is not in any special location in the universe. This process, sometimes called the Copernican principle, has been one of the great themes of scientific enlightenment. The KBC Void adds a twist to this story. We are not at the center of the universe, but we might be near the center of a vast empty region that makes our view atypical. We are not special in any cosmic sense, but our location might be unusual enough to bias our measurements. The universe does not revolve around us, but the universe we observe might look different from what an average observer would see. This is humbling in a different way than the traditional Copernican lesson. It suggests that even our most careful and sophisticated observations are shaped by factors we cannot control. We cannot choose where to place our telescopes, apart from the limited options available within our solar system. We observe from where we are, and where we are matters. Scientists deal with this through careful analysis and cross-checking of results. They compare measurements made in different directions, at different distances, using different techniques. If all the measurements agree, we gain confidence that our conclusions are robust. If they disagree, we look for explanations, either systematic errors in the measurements or real physical effects that cause the differences. The Hubble tension is a case where measurements disagree, and the void hypothesis is one possible explanation. It posits that the disagreement is not an error, but a consequence of our location in the cosmos. The local universe really does expand faster than the global average, because we are inside a giant bubble of relative emptiness where gravitational drag is reduced. If this explanation is correct, it teaches us something important about how to do cosmology. We cannot simply assume that local measurements represent global properties. We must account for the structure of the cosmos and how it affects our observations. The universe is not a perfectly uniform laboratory where every location gives the same results. It is a complex, structured environment where location matters. This lesson extends beyond the Hubble tension. As our measurements become more precise, we are likely to discover more anomalies and tensions. Some will be errors, some will be statistical flukes, but some might be genuine signatures of cosmic structure, clues that our models need to be refined. The void hypothesis also raises questions about how we should think about cosmic averages. When cosmologists talk about the average density of the universe or the global expansion rate, they are implicitly assuming that such averages are meaningful. But in a lumpy universe with large structures like voids and filaments, what does average even mean? There are different ways to define averages in a structured universe, and they do not always give the same answer. You can average over volume, counting each cubic megaparsec equally. You can average over mass, weighting by how much matter is present. You can average over observers, counting what a typical observer would measure. These different definitions can give different results, especially when the structure is pronounced. Cosmologists have developed sophisticated mathematical tools to handle these issues, but they are still working out the implications. The question of how to properly define and measure cosmic parameters in an inhomogeneous universe is an active area of research. Let us now consider some of the alternative explanations for the Hubble tension, beyond the void hypothesis. Understanding these alternatives helps put the void idea in context and shows how scientists are approaching this puzzling discrepancy. One possibility is systematic error in the measurements. Both the early universe and late universe methods involve complex chains of reasoning, with many steps where errors could creep in. Perhaps there is something wrong with how we calibrate the brightness of standard candles. Perhaps the physics of the early universe is slightly different from what we assume. Perhaps there are subtle instrumental effects that have not been fully accounted for. Scientists have spent years hunting for such errors, and so far they have not found any smoking guns. The measurements have been repeated with different instruments, different techniques, and different teams. The results keep coming back the same. This does not prove that systematic errors are absent, but it makes them less likely as the sole explanation. Another possibility is new physics beyond the standard model. The lambda CDM model assumes that dark energy behaves as a cosmological constant, with a fixed energy density that does not change over time. But what if dark energy is dynamic, evolving as the universe expands? This idea goes by various names, including quintessence or evolving dark energy. In these models, dark energy was stronger in the early universe and has weakened over time, or vice versa. Such evolution could affect the relationship between early and late universe measurements, potentially explaining the tension. Recent observations from DESI have provided tentative support for this idea. By measuring the expansion history of the universe with unprecedented precision, DESI found hints that dark energy might not be constant. If confirmed with more data, this would be a revolutionary discovery, overturning one of the key assumptions of modern cosmology. A related idea is early dark energy, which posits that a burst of dark energy-like behavior occurred shortly after the Big Bang, before the universe was even 1 million years old. This early boost would have altered the sound horizon, a key scale used to infer the expansion rate from the cosmic microwave background. By changing the sound horizon, early dark energy could reconcile the CMB predictions with local measurements. Early dark energy is theoretically plausible, fitting into certain extensions of particle physics, but it also faces challenges. It must be fine-tuned to act at just the right time and then disappear without a trace. Current observations have not definitively detected early dark energy, though they have not ruled it out either. Yet another possibility involves modifications to gravity. General relativity has passed every test we have thrown at it, from the bending of light around the sun to the gravitational waves from merging black holes. But on the largest cosmic scales, where dark energy dominates, the tests are less precise. Perhaps gravity behaves differently than Einstein predicted in these regimes. Theories of modified gravity, such as those involving massive gravitons or extra dimensions, can potentially explain the Hubble tension. But they also tend to have other consequences that should be observable, and so far these predictions have not been confirmed. Most cosmologists are cautious about abandoning general relativity without compelling evidence. Finally, there is the possibility that the Hubble tension is simply a statistical fluke. When you make many precise measurements, occasionally you will get results that disagree just by chance. The probability of this for the current tension is small, less than 1 in 1,000 according to most estimates, but not 0. Some researchers argue that we should not be too quick to invoke new physics when chance is a possible explanation. Each of these alternatives has proponents and critics. The debate is ongoing, with new data and new analyses appearing regularly. The void hypothesis is one contender among several, distinguished by its appeal to known structures rather than unknown physics. What makes the void hypothesis attractive to some scientists is its parsimony. It does not require any new particles, forces, or modifications to establish theories. It only requires that we take seriously the structure of the universe that we already know exists. Voids are real. The KBC Void in particular has been detected by multiple surveys. If it affects our measurements, that is not new physics. It is a consequence of existing physics applied to a real feature of the cosmos. On the other hand, skeptics point out that the void hypothesis makes specific predictions that can be tested. If we live in a void that biases our measurements, we should see certain signatures in the data. The bulk flows should have particular patterns. The CMB should show specific effects. The galaxy distribution should follow certain profiles. Some of these predictions match observations. Others are ambiguous. The jury is still out. Let us now dig deeper into the physics of how voids affect the light that travels through them. This is crucial for understanding why our measurements might be biased and how we could detect and correct for such biases. When light travels through the universe, it interacts with the matter and space-time it encounters. In a perfectly uniform universe, these interactions would be simple and predictable. But in a lumpy universe with voids and clusters, the light path is more complex. One effect is gravitational lensing. Mass bends space-time, and light follows the curves. When light passes near a massive object like a galaxy cluster, its path is deflected, sometimes dramatically enough to produce multiple images of a background source. Even without such spectacular effects, weak gravitational lensing subtly distorts the shapes of distant galaxies, providing a way to map the distribution of mass. Inside a void, there is less mass to bend light. Gravitational lensing is weaker, and light paths are straighter. This affects how we measure the distances to distant objects. If we use the shapes of background galaxies to infer the mass distribution, we might underestimate the mass in voids simply because the lensing signal is weaker. Another effect is the integrated Sachs-Wolf effect we mentioned earlier. When CMB photons pass through a void, they lose energy because the void is expanding. This makes the CMB appear slightly cooler in the direction of voids. By mapping these temperature variations and correlating them with known voids, astronomers can probe the properties of cosmic structure. A related effect involves the redshift of light from galaxies inside voids. Redshift has two components. The cosmological redshift comes from the expansion of the universe, stretching the light as it travels. The peculiar velocity redshift comes from the motion of the source galaxy relative to the cosmic expansion. Inside a void, galaxies are flowing outward toward the surrounding denser regions. This outflow adds to the cosmological redshift, making galaxies appear to recede faster than they would in a uniform universe. When we use redshifts to measure distances and calculate the Hubble constant, this extra component gets folded in, potentially biasing the result. Untangling these effects requires detailed modeling. You need to know the density profile of the void, the velocity field of the galaxies, and the paths that light takes through the structure. With these ingredients, you can calculate how much each effect contributes to the observed quantities and potentially correct for the bias. This is exactly what researchers are trying to do. By building models of the KBC Void and comparing them to observations, they aim to quantify the impact on cosmological measurements. If the models work, they could not only explain the Hubble tension, but also provide a template for correcting future observations. There is another subtlety worth mentioning. The KBC Void is not perfectly spherical or perfectly centered on the Milky Way. Its shape is irregular, influenced by the surrounding cosmic web, and our position within it is off-center, closer to one wall than another. This asymmetry means that the void's effects are not uniform across the sky. In some directions, we are looking through more of the void. In others, we are looking toward the denser walls. This should produce variations in our measurements depending on which way we point our telescopes. Such variations, if detected, would be powerful evidence for the void hypothesis. They would show that our view of the universe is direction dependent, exactly as you would expect if we are inside an asymmetric structure. So far, some studies have found hints of such variations, while others have not. The signal, if present, is subtle and requires large datasets to extract reliably. The anisotropy of the void also provides a potential test that could distinguish the void hypothesis from other explanations for the Hubble tension. New physics, like evolving dark energy or modified gravity, would typically produce effects that are uniform across the sky. But the void hypothesis predicts direction-dependent effects. By carefully comparing measurements in different parts of the sky, astronomers could potentially rule one explanation in or out. This is the kind of test that upcoming surveys are designed to perform. With their wide sky coverage and deep observations, they will map the cosmos in enough detail to detect or exclude direction-dependent signals. The next decade of observations could be decisive. Let us pause and consider what the void story tells us about the nature of scientific discovery. The KBC Void is not a dramatic find like a new particle or a groundbreaking equation. It is a subtle feature of cosmic structure, the kind of thing that only emerges from careful analysis of large datasets. Yet its implications could be profound. Science often advances not through eureka moments, but through patient accumulation of evidence. You measure something. You compare it to expectations. You notice a small discrepancy. You investigate possible explanations. You gather more data. Slowly, a picture emerges. The Hubble tension follows this pattern. It started as a minor disagreement between measurements, not significant enough to worry about. But as the data improved, the discrepancy persisted. Scientists began to take it seriously and propose explanations. The void hypothesis emerged as one possibility among several. We do not yet know which explanation is correct. Maybe none of the current ideas will survive scrutiny. Maybe the answer is something no one has thought of yet. That is how science works. You follow the evidence, test your ideas, and remain open to surprises. The void hypothesis has the virtue of being testable. It makes specific predictions that can be checked with better data. If the predictions hold up, the hypothesis gains credibility. If they fail, the hypothesis is weakened or ruled out. Either outcome advances our understanding. This is the essence of the scientific method. You propose ideas that can be proven wrong and then try to prove them wrong. The ideas that survive this gauntlet of testing are the ones we provisionally accept as true, until better evidence comes along. In the case of cosmic voids, the testing is still underway. The outcome could go either way. But whatever happens, we will learn something important about the universe and our place in it. Now let us turn to a different aspect of the void story, one that touches on questions of existence and meaning. What does it mean, philosophically and personally, to live inside a cosmic void? On one level, it changes nothing about our daily lives. Whether we are in a void or a filament, the sun still rises, seasons still change, and life goes on. The cosmic structures are so vast and so far removed from human scales that they have no practical impact on anything we do. But on another level, the void raises questions about cosmic significance. We like to think that we are part of something larger, connected to the grand sweep of cosmic history. The idea that we inhabit an empty backwater, a gap between the real action, can feel deflating. Yet consider another perspective. Voids are the largest structures in the universe by volume. If you were to randomly drop a point into the cosmos, it would most likely land in a void. In that sense, voids are not unusual. They are the typical environment of the universe. We are not in a special place. We are in a common place. Moreover, the void is not truly empty. It contains our galaxy and billions of others. It contains stars and planets, and at least on one small world, life. The emptiness is relative, a matter of degree compared to the cosmic average. By any human standard, the void is unimaginably full. There is also something to be said for the perspective that emptiness provides. From within a void, we can see farther into the cosmos because there is less intervening matter to block our view. The cosmic microwave background, the oldest light in the universe, reaches us relatively unobstructed. We have a clearer window onto cosmic history than observers in denser regions might have. This is a bit like living on a mountaintop versus living in a valley. The mountaintop is exposed and lonely, but the view is spectacular. The void is our cosmic mountaintop, giving us a panoramic vista of the universe's structure and evolution. Some scientists have speculated about whether voids might be friendlier to life than denser regions. In the dense environments of galaxy clusters, stars are closer together, and the chances of disruptive gravitational encounters or radiation bursts might be higher. In a void, stars are more isolated, and the cosmic neighborhood is quieter. Perhaps life has more time to develop and evolve in such tranquil settings. This is speculative, of course. We have no evidence that life is more or less common in voids than elsewhere. The factors that make a planet habitable are complex, and cosmic environment is just one of many considerations. But it is an interesting thought, connecting the grandest scales of cosmology to the intimate question of where life can flourish. There is a philosophical tradition that finds meaning in emptiness. Buddhist concepts of sunyata, or emptiness, teach that things have no inherent existence apart from their relationships and conditions. The void of space, with its lack of stuff but abundance of potential, resonates with this perspective. The cosmic void is not nothing. It is space itself, with all its quantum fluctuations and dark energy. It is the canvas on which matter paints its patterns. Without the void, there would be no contrast, no structure, no cosmic web. The emptiness is as essential to the universe as the fullness. Perhaps living in a void teaches us something about the value of space, of room to grow and explore. The dense regions of the cosmos are crowded and chaotic. The voids are open and expansive. There is beauty and possibility in both. These philosophical musings do not prove anything, of course, but they remind us that science is not just about numbers and equations. It is also about meaning and wonder, about connecting the facts we discover to the lives we live. The void is a scientific concept, but it is also a metaphor, an invitation to reflect on our relationship to the vast and mysterious cosmos. Let us return to the hard science and explore more deeply the evidence that astronomers have gathered about our cosmic neighborhood. Understanding this evidence is crucial for evaluating whether the void hypothesis can truly explain the Hubble tension. The first clue comes from counting galaxies. When astronomers survey the sky and catalogue the positions of millions of galaxies, they find that the number density is not uniform. Some regions are packed with galaxies, others are sparse. By measuring these variations, we can map the large-scale structure of the cosmos. Multiple surveys have found that the region around the Milky Way, out to distances of about 1 billion light-years, contains fewer galaxies than the cosmic average. The deficit is roughly 20 to 30%, meaning we live in a region that is significantly less crowded than typical. This underdensity shows up in surveys at different wavelengths. Optical surveys, which count galaxies by their visible starlight, show the deficit. Infrared surveys, which penetrate dust and detect redder light, show it too. Even X-ray surveys, which map the hot gas in galaxy clusters, find fewer clusters than expected in our neighborhood. The consistency across different types of observations strengthens the case that the underdensity is real. If it were an artifact of one particular measurement technique, you would not expect it to appear in all the data. The fact that it does suggests we are looking at a genuine feature of cosmic structure. Another piece of evidence comes from measuring the flow of galaxies. As we discussed, galaxies in a void experience a gravitational pull toward the surrounding denser regions. This creates a systematic outflow, a bulk motion that can be detected by measuring galaxy velocities. The Cosmic Flows surveys have measured the velocities of tens of thousands of galaxies using various techniques. One method involves Tully-Fisher relations, which connect the rotation speed of spiral galaxies to their luminosity. Another uses type Ia supernovae, whose intrinsic brightness is well calibrated. By comparing observed brightness to known luminosity, astronomers can determine distances, and by comparing distances to redshifts, they can infer velocities. The results showed that galaxies in our neighborhood are indeed flowing outward, away from underdense regions and toward overdense ones. The flow pattern is complex, influenced by multiple structures like the Shapley concentration and the Great Attractor. But the overall picture is consistent with what you would expect if we were inside a large void. Interestingly, the observed flows are stronger than what the standard cosmological model predicts. In a perfectly homogeneous universe, bulk flows should be relatively modest, but the observed flows extend over hundreds of millions of light years and reach velocities of several hundred kilometers per second. This excess flow, sometimes called the bulk flow anomaly, is another tension with the standard model that the void hypothesis could potentially explain. A third line of evidence involves the cosmic microwave background. The CMB is remarkably uniform, with temperature variations of only about 1 part in 100,000 across the sky. But within this uniformity, there are subtle patterns that encode information about cosmic structure. One such pattern is the integrated Sachs-Wolf effect, which we have mentioned several times. When CMB photons traverse a void, they lose energy because the void is expanding. This creates a cold spot in the CMB in the direction of the void. Astronomers have searched for correlations between CMB temperature variations and the positions of known voids. Several studies have found evidence for such correlations, with the CMB appearing cooler in directions where voids are present. This supports the idea that voids are real, expanding structures that affect the light passing through them. One famous example is the CMB cold spot, a region in the southern sky where the temperature is noticeably lower than average. This cold spot was discovered in data from the WMAP satellite and confirmed by Planck. It is larger and colder than typical fluctuations, making it statistically unusual. Some researchers have proposed that the cold spot is caused by a supervoid along that line of sight. By analyzing galaxy surveys in the cold spot direction, they have found evidence for an underdense region that could produce the observed temperature decrement. If correct, this would be a direct detection of a void's effect on the CMB. However, the interpretation remains controversial. Other researchers argue that the cold spot can be explained by primordial fluctuations without invoking a supervoid. The galaxy data in that region are incomplete, and the significance of the proposed void is debated. More observations are needed to settle the question. The KBC Void itself is not directly visible in the CMB because we are inside it. You cannot see the forest when you are standing among the trees, but the void should affect the CMB in more subtle ways, altering the statistical properties of the fluctuations we observe. Detecting such effects requires sophisticated analysis and large datasets. A fourth type of evidence involves supernovae. Type IR supernovae are used as standard candles to measure distances in the universe. By comparing their observed brightness to their known luminosity, astronomers can determine how far away they are. Combined with redshift measurements, this gives the expansion rate. If we live inside a void, the supernova we observe should show certain patterns. Those inside the void would be affected by the void's peculiar velocity field. Those outside would have their light bent and stretched as it passes through the void. By carefully analyzing a large sample of supernovae, you could potentially detect these effects. Some studies have looked for evidence of void effects in supernova data. The results are mixed. Some analyses find hints of a local underdensity consistent with the KBC Void. Others find no significant deviation from a homogeneous universe. The challenge is that the effects are small, and the supernova samples, while large, are still limited by measurement uncertainties. The James Webb Space Telescope is now contributing to this effort. By observing Cepheid variable stars and supernovae with unprecedented precision, Webb can calibrate the distance ladder more accurately than ever before. Its recent results have confirmed that the Hubble measurements from the Hubble Space Telescope are correct, ruling out certain types of systematic errors. But the Hubble tension remains, and the void hypothesis is still on the table. Let us now synthesize all this evidence and consider what it tells us about the likelihood of the void hypothesis. On the positive side, there is clear evidence that the local universe is underdense. Galaxy counts, bulk flows, and CMB analyses all point in the same direction. The KBC Void appears to be a real feature of cosmic structure, not a measurement artifact. Furthermore, the properties of the void are roughly consistent with what would be needed to explain the Hubble tension. The size, depth, and location of the underdensity are in the right ballpark to produce a local expansion rate that is about 10% higher than the cosmic average. On the negative side, the evidence is not conclusive. The measured properties of the void have significant uncertainties. Different surveys give somewhat different answers about the void's size and depth, and some analyses find no evidence for a void at all, arguing that the local universe is consistent with homogeneity. Moreover, the void hypothesis makes predictions that have not been fully verified. If we are inside a void, we should see specific signatures in the data, like direction-dependent variations in the Hubble constant. Some studies have looked for these signatures without finding clear evidence. Others have found hints that are not statistically compelling. The bottom line is that the void hypothesis is plausible but not proven. It remains one of several competing explanations for the Hubble tension, along with systematic errors, new physics, and statistical fluctuations. More data and more careful analysis are needed to determine which, if any, of these explanations is correct. This uncertainty is frustrating but also exciting. We are at the frontier of knowledge, where the evidence is incomplete and the truth is not yet clear. This is exactly where scientific breakthroughs happen. By pushing harder on the data and testing our ideas rigorously, we inch closer to understanding. Whatever the outcome, the void hypothesis has already made a contribution. It has reminded cosmologists that the assumption of homogeneity cannot be taken for granted. It has stimulated new analyses and new ways of thinking about cosmic structure. And it has highlighted the importance of understanding our location in the universe, not just for its own sake, but for interpreting all our observations. Now let us explore what happens if we take the void hypothesis seriously and project into the future. If we truly live in a cosmic void that affects our measurements, What does that mean for the evolution of our cosmic neighborhood? We have already discussed how voids grow over time, expanding and emptying as matter flows to the surrounding denser regions. The KBC Void, like all voids, is getting bigger. The walls that bound it are receding, carried by the expansion of space and pushed by the outflow of matter. This growth has implications for what we will be able to see in the distant future. As the void expands, galaxies outside it will be carried farther away. The light from those galaxies will have to travel longer distances to reach us, and it will be stretched further by the expanding space. Eventually, galaxies that are now visible will cross the cosmological horizon and disappear from view. Their light will no longer be able to reach us because the space between us is expanding faster than light can traverse it. We will become increasingly isolated, surrounded by an ever-growing ocean of emptiness. This cosmic isolation is part of the general fate of the universe under accelerated expansion. Dark energy is pushing everything apart, and the long-term trend is toward loneliness. But if we are already inside a void, this isolation may come sooner for us than for observers in denser regions. The walls of our void are already far away and getting farther. In the very long term, the only galaxies we will be able to see are those that are gravitationally bound to us, the members of our local group. The Milky Way, Andromeda, and their small companions will merge into a single large galaxy, floating in a vast dark emptiness. All the other galaxies in the universe will be gone from view, hidden beyond unreachable horizons. This is a melancholy picture, but it is also inconceivably far in the future. The timescale for this isolation is billions of years, far longer than any human civilization can reasonably plan for. In the meantime, the universe remains gloriously full of galaxies to study and explore. Let us now consider the implications of the void for our understanding of dark energy. This mysterious force is the main driver of the accelerated expansion that will ultimately isolate us. Understanding dark energy is one of the central goals of modern cosmology. As we have discussed, the leading candidate for dark energy is the cosmological constant, a uniform energy density that permeates all of space. In this model, dark energy has the same strength everywhere and at all times. Its effects are the same in voids as in clusters, in the past as in the present. But if dark energy interacts with cosmic structure in more complex ways, the picture could be different. Some theories propose that dark energy behaves differently in different environments, perhaps being stronger in voids, where there is less matter to interact with. Such models could produce different expansion rates in different regions, potentially contributing to the Hubble tension. Alternatively, dark energy might be evolving over time, rather than constant. The DESI results we mentioned earlier suggest that dark energy may have been stronger in the past and is weakening today, or vice versa. If this is confirmed, it would revolutionize our understanding of the universe's dynamics. The void provides a unique laboratory for studying dark energy. Because voids are dominated by dark energy rather than matter, they are the places where dark energy's effects are most clearly visible. By carefully observing how voids evolve, astronomers can test models of dark energy and constrain its properties. This is not easy. Voids are hard to observe precisely because they are empty. There are few galaxies inside them to serve as tracers. The measurements are challenging and the uncertainties are large, but the potential payoff is enormous. Understanding dark energy would answer one of the deepest questions in physics. What is driving the universe to tear itself apart? The void hypothesis sits at the intersection of several major puzzles in cosmology. It connects the Hubble tension, the nature of dark energy, the formation of cosmic structure, and the ultimate fate of the universe. Solving any one of these puzzles could advance our understanding of the others. This is why so many scientists are interested in voids, despite their emptiness. The nothing is not nothing. It is a window into the fundamental workings of the cosmos. Let us now bring our discussion full circle and consider what all this means for the title of our exploration. The cosmic void is breaking the universe, or so we have said. But what does breaking really mean in this context? In one sense, the void is breaking our models. The standard lambda CDM model assumes a homogeneous universe, but the void suggests that homogeneity may not hold on the larger scales. If the void is real and affects our measurements significantly, it means our models need revision. The pristine mathematical framework that has guided cosmology for decades may need to be patched or even rebuilt. In another sense, the void is breaking the universe apart. The expansion driven by dark energy, amplified in the void, where there is little matter to resist it, is carrying structures away from each other. Filaments are stretching. Clusters are separating. The cosmic web is being pulled apart at its seams. This is a slow breaking, taking billions of years, but it is happening nonetheless. In yet another sense, the void is breaking our perception. We thought we had a clear view of the cosmos, an objective window into the workings of the universe. But the void suggests our view may be biased, shaped by our location in an atypical region. The universe we see may not be the universe that is. This is a humbling break, a crack in our epistemological confidence. All of these breakings are connected. They stem from the same underlying reality. The universe is not the simple, uniform place that our earliest models imagined. It is complex and structured, full of variations that matter. Understanding these variations is essential for understanding everything else. The void is not a flaw or an aberration. It is part of the natural evolution of the cosmos, a consequence of how gravity and dark energy sculpt matter over billions of years. Every void, including the one we inhabit, tells a story about the history and future of the universe. Reading that story is one of the great projects of modern science. And what a story it is. From the quantum fluctuations in the first fraction of a second, to the formation of the cosmic web over billions of years, to the accelerated expansion that will eventually isolate galaxies in the far future. The universe is a dynamical arena of constant change. We are privileged to witness a moment in this grand evolution, to see the cosmos in its present state before it transforms into something else. The void we inhabit is part of this story. It shapes what we see and how we understand our place in the universe. It connects us to the larger structures in existence and to the deepest mysteries in physics. It reminds us that the cosmos is far stranger and more wonderful than we could have imagined. In exploring the void, we are not just doing astronomy. We are grappling with fundamental questions about reality, knowledge, and existence. What is the universe made of? How do we know what we know? What does it mean to be a conscious being in a vast and evolving cosmos? These questions do not have easy answers, but asking them is part of what makes us human. We are the universe becoming aware of itself, looking out at the stars and wondering what it all means. The void, in its emptiness, invites us to fill it with meaning through our curiosity and our imagination. So where does this leave us? We have journeyed through the cosmic web, explored the nature of voids, examined the evidence for the KBC Void, and considered what it means to live in an emptiness that might be altering our view of the universe. We have touched on dark energy, the Hubble tension, and the ultimate fate of all things. Now it is time to bring everything together and confront the central claim of our exploration. The universe is not just expanding, it is being warped by its own internal structure. The very emptiness we inhabit is pushing the boundaries of physics, forcing us to question our core models of the cosmos. The void is not passive. It is an engine of expansion, of isolation, and perhaps of scientific revolution. This is the climax of our story. The realization that the place we call home, the cosmic address we never chose, might be fundamentally reshaping our understanding of everything. Consider what is at stake. The Hubble constant is not just a number. It encodes the age of the universe, the distances to faraway galaxies, and the ultimate fate of cosmic expansion. If our local measurement is biased by the void, then our calculations of all these things might be off. The universe might be older or younger than we thought. Galaxies might be closer or farther. The future might unfold differently than we predicted. The standard model of cosmology, lambda CDM, has been one of the great achievements of modern science. It explains observations ranging from the cosmic microwave background to the distribution of galaxies to the abundances of light elements. It has made predictions that have been confirmed time and time again. It gives us a coherent picture of a universe that began in a hot Big Bang, expanded and cooled, formed stars and galaxies, and is now accelerating toward a cold, dark future. But the Hubble tension is a crack in this edifice. It suggests that something is not quite right. Either our measurements are wrong, or our model is incomplete. Scientists are working hard to figure out which. The void hypothesis offers one possible resolution. It says that the model is mostly correct, but our local environment is unusual. We live in a bubble of emptiness that makes our measurements atypical. The tension arises not from flawed physics, but from our peculiar vantage point. If this is true, it would be both reassuring and unsettling. Reassuring because it means lambda CDM can survive without major revision. Unsettling because it means we have to accept that our view of the cosmos is biased in ways we did not expect. But there are other possibilities. Perhaps dark energy is not constant but evolving. Perhaps gravity behaves differently on cosmic scales than Einstein predicted. Perhaps there are new particles or fields that we have not yet discovered. Any of these would be revolutionary, overturning assumptions that have guided physics for decades. The stakes could not be higher. We are talking about the fundamental nature of reality, how the universe works, what it is made of, where it came from and where it is going. And here we are, tiny creatures on a small planet orbiting an ordinary star in an undistinguished galaxy in a cosmic void, trying to figure it all out. The audacity of it is breathtaking. The humility required is profound. Let us now consider what all this means for humanity right now. Does living in a cosmic void affect our daily lives? Does the Hubble tension change anything about how we go about our business? In the immediate practical sense, the answer is no. The cosmic structures we have been discussing are so vast and so remote that they have no direct impact on anything we do. The expansion of the universe does not affect the Earth's orbit or the weather or the economy. The void does not make your commute longer or your coffee less satisfying. But in a deeper sense, the answer is yes. Understanding our place in the cosmos changes how we think about ourselves and our world. It shapes our sense of possibility and our awareness of the larger context in which our lives unfold. Knowing that we live in a cosmic void, if indeed we do, is part of the grand project of self-understanding that has driven human inquiry for millennia. We want to know where we are, not just on a map of Earth, but on a map of everything. The void is part of that map, a feature of reality that we are only beginning to understand. Moreover, the scientific questions raised by the void have practical implications for the future of astronomy. The telescopes and surveys being built to study cosmic structure will generate knowledge and technology that benefit society in ways we cannot fully predict. The pursuit of fundamental understanding often leads to unexpected applications, from the GPS satellites that rely on general relativity to the medical imaging technologies that grew out of particle physics. The void also raises questions about the long-term future of civilization. If we are destined for cosmic isolation, cut off from most of the universe by the accelerating expansion, what does that mean for any descendants we might have billions of years from now? These are speculative questions, far beyond any practical planning horizon. But they are part of the context in which we exist, the grand narrative of which our lives are a small chapter. For now, the most important implication is intellectual. The void and the tensions it raises are pushing scientists to think harder and more creatively about the cosmos. New theories are being proposed, new observations are being planned, new tools are being developed. The frontier of knowledge is advancing, driven by the stubborn discrepancy between what we expect and what we observe. This is how science progresses, not by confirming what we already believe, but by confronting anomalies that challenge our understanding. The Hubble tension is one such anomaly. The void is one possible explanation. Whether it turns out to be correct or not, the process of investigation will teach us something valuable. Let us take a moment to appreciate the journey we have been on. We started with a provocative question. Is our existence within a cosmic emptiness causing the universe to accelerate toward destruction? We have explored that question from many angles, examining the structure of the cosmic web, the physics of voids, the mystery of dark energy, and the measurements of cosmic expansion. We have learned that the universe is not a smooth, uniform expanse, but a complex network of filaments and voids shaped by gravity and dark energy over billions of years. We have seen that voids are not just empty spaces but dynamic regions where the expansion proceeds differently than in denser areas. We have considered the possibility that our location in such a void biases our observations and creates tensions with our theoretical models. We have also encountered uncertainty. The evidence for the KBC Void is suggestive but not conclusive. The void hypothesis is plausible but not proven. Scientists are still debating and investigating, seeking the data that will settle the question one way or another. This uncertainty is not a weakness, but a strength of science. It reflects the honest acknowledgement that we do not yet know everything. It keeps us open to new ideas and new evidence. It ensures that our conclusions are provisional, subject to revision as we learn more. The void reminds us that the universe is full of surprises. Just when we think we have it figured out, something new comes along to challenge our assumptions. This is frustrating but also exhilarating. It means there is always more to discover, always another mystery waiting around the corner. As we bring our exploration to a close, let us reflect on what it means to be conscious beings in such a universe. We are made of atoms forged in ancient stars, organized by billions of years of evolution into creatures that can wonder about their own origins. We look out at the cosmos and see vastness, complexity, and beauty beyond measure. The void is part of this beauty. It is the space between things, the canvas on which the cosmic web is painted. Without voids, there would be no structure, no contrast, no filaments, reaching across the darkness. The emptiness is as essential as the fullness, and within this void, on a small blue planet, life has taken root. Minds have emerged that can contemplate the void, measure it, theorize about it, and share their discoveries with others. This is remarkable. This is precious. This is, as far as we know, unique in all the cosmos. The void does not care about us. It has no intentions, no plans, no awareness. It is just space expanding according to the laws of physics. But we care about the void. We find meaning in understanding it. We connect with something larger than ourselves by contemplating its vastness. This is the human project, to make sense of a universe that does not owe us any explanations, to find beauty and meaning in the cold equations of physics, to keep asking questions even when the answers are hard to come by. The cosmic void is breaking the universe in the sense that it is tearing apart the cosmic web and challenging our models. But it is also building something. It is building our knowledge, our sense of wonder, our connection to the grand story of existence. We are inside the void, but the void is also inside us. The atoms in our bodies came from stars that formed in regions shaped by cosmic structure. The thoughts in our minds are shaped by questions that arise from contemplating that structure. We are products of the void's evolution, and we are agents in its ongoing story. As you lie in bed tonight, drifting towards sleep, consider this. The darkness you see when you close your eyes is a tiny echo of the cosmic darkness that surrounds our island of stars. But within that darkness, galaxies are forming, stars are burning, and somewhere, perhaps, other minds are looking up at their own skies and wondering the same things you wonder. The void connects us all. It is the common ground of the cosmos, the shared space in which everything exists. In contemplating the void, we are contemplating our own place in the universe, our own relationship to everything that is. And what a place it is. Not the center, not the edge, but somewhere in between. Not special, not typical, but unique in its own way. Not permanent, not fleeting, but somewhere in the long arc of cosmic time. We are here now, in this void, in this moment, alive and aware and full of questions. The universe does not answer our questions directly. It offers clues, hints, puzzles that we must work to solve. The void is one such puzzle. The Hubble tension is another. The nature of dark energy, the fate of the cosmos, the origin of structure. All of these are questions that await answers. Some of these answers may come in our lifetimes. New telescopes like the James Webb Space Telescope, Euclid, and the Vera Rubin Observatory are gathering data that will shed light on the mysteries we have discussed. New theories are being developed that may resolve the tensions and extend our understanding. The pace of discovery is accelerating, even as the universe itself accelerates apart. Other answers may take longer. The deepest questions about the cosmos may require centuries of work, or they may remain forever beyond our reach. The universe is under no obligation to be comprehensible. We are lucky that it is as comprehensible as it is. But whether the answers come quickly or slowly, the pursuit is worthwhile. Understanding the cosmos is one of the noblest things human beings can do. It expands our horizons, enriches our culture, and connects us to something infinitely greater than our individual lives. The void invites this pursuit. It challenges us with its vastness, its emptiness, its strange effects on the light that travels through it. It asks us to rise to the occasion, to build bigger telescopes, develop better theories, and push the boundaries of what we know. And so we will. As long as there are curious minds on this planet, we will keep looking up at the stars and asking what lies beyond. We will keep measuring the expansion of the universe and trying to understand what drives it. We will keep exploring the cosmic web, mapping its filaments and voids, and figuring out how they shape the cosmos. The void may be empty, but our response to it is full of meaning. In the face of cosmic indifference, we create purpose through inquiry. In the vastness of space, we find our own significance by seeking to understand it. This has been a journey through one of the strangest and most profound ideas in modern cosmology. The idea that we live in a cosmic void that is breaking the universe, or at least breaking our understanding of it. We have explored the evidence, the theories, the implications, and the open questions. We have seen how much we know and how much remains to be discovered. As you go about your life, remember this: you are part of something vast and ancient and ongoing. The atoms in your body were forged in stars. The planet you stand on orbits a star in a galaxy, in a void, in a cosmic web, in an expanding universe. You are connected to all of it through the laws of physics that govern everything from the smallest particle to the largest structure. The void is your home, as strange as that may sound. It is where you were born, where you live, and where your descendants, if any, will continue the human story. It is not a welcoming place in the conventional sense. It is cold and vast and mostly empty, but it is ours. It is where we get to exist and wonder and explore. So the next time you look up at the night sky, remember the void. Remember that between the stars you see, there are vast, empty spaces. Remember that our galaxy floats in one of those spaces, a region of relative emptiness in a universe full of structure. Remember that this emptiness might be affecting how we see everything else, biasing our measurements and challenging our models. And remember that despite all this, we persist. We keep asking questions. We keep building telescopes. We keep pushing back the boundaries of the unknown. This is what we do. This is who we are. The cosmic void is breaking the universe, and we are inside it, watching, measuring, wondering, and trying to understand. In that act of understanding, we find our place in the cosmos, not at the center, not at the edge, but right where we are, in the void, at home. The emptiness stretches in all directions, vast beyond comprehension, dark beyond imagining. Yet here we are, points of light in the darkness, minds in the midst of mindless expansion. The void has produced us, shaped us, and now challenges us to understand it. We accept that challenge. We embrace it, because that is what it means to be human in a universe that is far stranger, far more beautiful, and far more mysterious than we ever dared to dream. And with that thought, let this cosmic journey come to a gentle close. The void surrounds you, but you are not alone. Billions of other humans share this moment with you. Billions of stars shine in the darkness. And somewhere out there, the answers to our deepest questions wait to be discovered. The universe keeps its secrets, but not forever. One day, perhaps, we will understand why the void is breaking the universe. Until then, we wonder. And in wondering, we find our meaning. There is one more aspect of this cosmic story that deserves our attention before we truly conclude. It concerns the relationship between scientific discovery and human meaning. Throughout history, advances in our understanding of the cosmos have changed how we see ourselves. Each revelation has been both humbling and elevating, diminishing our sense of centrality while expanding our sense of wonder. When Copernicus proposed that the Earth orbits the Sun rather than the other way around, It removed humanity from the center of the solar system. When astronomers realized that our sun is just one of billions in the Milky Way, it removed us from the center of our galaxy. When we discovered that the Milky Way is just one of trillions of galaxies in the Observable Universe, it removed us from the center of the cosmos entirely. The void hypothesis continues this tradition. It suggests that not only are we not at the center of anything special, but we are in a region of space that is below average in density. We inhabit the cosmic suburbs, if not the outskirts. The bustling metropolises of the universe, the dense clusters and superclusters where galaxies crowd together, are far from here. We live in the quiet countryside, where the neighbors are few and far between. Yet each of these discoveries has also elevated us in a different sense. By revealing the true scale and complexity of the universe, they have shown us just how remarkable our existence is. Against all the vast emptiness and hostile environments of space, life has somehow emerged and flourished on this small world. Consciousness has arisen, capable of contemplating the cosmos that produced it. This is extraordinary, regardless of where in that cosmos we happen to be located. The void, for all its emptiness, is the womb that gave birth to us. The conditions here, whatever they are, allowed the Milky Way to form and evolve in relative peace. Our solar system coalesced from a cloud of gas and dust that drifted through this region of space. Life arose on Earth and developed the complexity that eventually produced minds like ours. All of this happened in the void, because of the void, or at least despite the void. Perhaps the emptiness is not a disadvantage, but an advantage. Perhaps the relative quiet of a void allows for more stable conditions, fewer disruptive events, more time for evolution to work its slow magic. This is speculation, but it is worth considering. The universe is not random. The structures that form, the locations that become hospitable to life, the circumstances that allow intelligence to emerge, all of these are constrained by the laws of physics operating on the matter and energy that exist. If we are here in this void, perhaps there is a reason related to the very properties of voids that made our existence possible. Or perhaps not. Perhaps our location is simply an accident of cosmic history, a random throw of the dice that landed us here rather than somewhere else. The universe is vast enough that somewhere within it, conditions were bound to be right for life. We are here because here is where those conditions happen to occur. There may be no deeper meaning to extract. Either way, the void invites reflection. It asks us to consider what it means to exist in the place we do, at the time we do, with the knowledge we have. It challenges us to find significance not in our location, but in our response to that location. We cannot choose where we are born in the cosmos. We can choose what we do with our awareness of that birthplace. The scientists who study the void are engaged in one such response. They are using their intellects and their instruments to probe the mysteries of cosmic structure. They are asking how the universe works and what it is made of. They are building the knowledge that will benefit future generations, even if those generations live in a cosmos that has continued to expand and change. This scientific endeavor is a deeply human activity. Other animals do not study the cosmos. They do not build telescopes or develop theories or debate the Hubble tension. Only humans, as far as we know, engage in this kind of systematic inquiry into the nature of reality. It is one of the things that makes us unique, one of the contributions we can make to the universe that produced us. In studying the void, we are the void becoming aware of itself. We are the cosmos examining its own structure, asking questions about its own nature. This is a profound and perhaps even sacred activity, regardless of whether one frames it in religious or secular terms. The universe has given rise to beings who can understand it. That understanding is a gift we give back to the universe, a completion of a circle that connects us to everything. The void does not know that we are here. It does not know anything. It is just space, following the equations of physics, expanding according to the rules that govern everything. But we know that it is here. We know that we are inside it. And in knowing, we transform mere existence into experience, mere structure into meaning. This is what consciousness does. It takes the raw material of the universe and weaves it into stories, theories, questions, and answers. The void is part of that raw material. Our exploration of it is part of the weaving. The result is the tapestry of human knowledge, growing richer and more detailed with each passing generation. The next generation of astronomers will know more about the void than we do. They will have better data, better models, better tools. They will answer some of the questions we cannot answer and discover new questions we have not even imagined. The pursuit of understanding never ends. Each answer opens new doors to new mysteries. This is exciting rather than discouraging. It means that the cosmic story is still being written, and we are among its authors. Our observations, our theories, our debates, all of these contribute to the ongoing narrative. Future historians of science will look back at our time and see what we discovered, what we got right, and what we got wrong. They will build on our work, correcting our mistakes and extending our insights. The void will be part of that legacy. Whether the void hypothesis turns out to be correct or not, it will have played a role in the development of cosmological thought. It raised important questions about homogeneity and local structure. It stimulated new observations and new analyses. It reminded scientists to be humble about their assumptions. All of this has value, regardless of the ultimate verdict. Science advances by proposing ideas and testing them. Some ideas pass the tests and become established knowledge. Others fail and are discarded. But even the failures contribute by narrowing the space of possibilities and pointing toward better ideas. The void hypothesis, whatever its fate, is part of this process. It is science in action. As we truly conclude now, consider the vastness of what we have explored. We started with a single question about the void and ended up touching on the entire history and structure of the universe. We discussed quantum fluctuations in the first fraction of a second, the formation of the cosmic web over billions of years, the mysterious nature of dark energy, the puzzling Hubble tension, and the far future fate of all existence. We connected these cosmic themes to human concerns about meaning, knowledge, and our place in the grand scheme of things. This is the power of a good question. It leads you on a journey far beyond its original scope. It connects seemingly disparate topics into a coherent narrative. It reveals the deep interconnections that underlie reality. The void is such a question. What does it mean to live in a cosmic void? The answer touches on physics, astronomy, philosophy, and the human condition. It cannot be answered in a single sentence or a single study. It requires the collective effort of thousands of scientists over decades, combining observations, theories, and debates to slowly approach the truth. We are part of that collective effort. By learning about the void, by caring about the questions it raises, by sharing this knowledge with others, we contribute to the human project of understanding. We are not passive observers of the cosmos. We are active participants in its self-reflection. The void is vast and empty, but our response to it fills it with meaning. The universe is cold and indifferent, but our curiosity warms it with purpose. The cosmos is ancient and endless, But our brief moment within it matters because we make it matter, and so we end where we began, with the wonder that drives all inquiry. The cosmic void is breaking the universe, challenging our models, and inviting us to think harder about everything we thought we knew. We accept that invitation. We embrace the challenge. We are creatures of the void, born in emptiness, reaching toward understanding. The stars will continue to shine. The galaxies will continue to recede. The void will continue to expand. But as long as there are minds to wonder, the cosmos will never be truly empty. Our questions fill the void. Our curiosity lights the darkness. Our existence gives the universe someone to know it. That is the deepest lesson of the void. In the midst of vast emptiness, consciousness arises and makes everything meaningful. We are small and brief and lost in immensity, but we are here. We are aware, and we will never stop wondering about the strange and beautiful universe that made us possible. The night sky calls to us, as it has called to every generation before us. The same stars that guided ancient sailors and inspired ancient myths are the stars we see tonight, though we now know them to be distant suns surrounded by their own worlds. The same darkness between the stars that terrified our ancestors is the darkness we now recognize as the cosmic void, a feature of the universe's grand structure rather than a mere absence of light. We have traveled far in our understanding since those ancient times. We have measured the distances to galaxies billions of light years away. We have detected the afterglow of the Big Bang itself. We have discovered that the universe is expanding, and that this expansion is accelerating. We have mapped the cosmic web and identified the voids that punctuate it. We have found our place in this vast structure, somewhere near the center of one of those voids, looking out at a cosmos that may appear different to us than it would to observers elsewhere. All of this knowledge has come from human curiosity, human ingenuity, and human persistence. It represents countless hours of observation, calculation, and debate. It is a testament to what our species can achieve when we dedicate ourselves to understanding rather than mere survival. The void will continue to expand. The universe will continue to evolve. But so will our understanding. The story is not over. The bee we wonder.